Can I start? Okay, right. Thank you for inviting me. It's really nice to talk to hear on the research that I'm doing and give you some flavor of where things are currently in high energy physics and what people are thinking about and worried about. Okay, so to start, people have to give you a little bit of a crash course in quantum field theory. Okay, so you're going to learn everything about quantum field theory in 2 minutes. So let me start with some remarks on quantum field. And actually what I want to comment or remark on is actually a modern way of thinking about quantizing the system. I don't think any of you, or maybe some of you, have been exposed to the idea of path or functional independence. Has anybody heard about that concept? Some people have. But let me just briefly introduce you to how we think about quantizing a system in a way. So the starting point of any quantum independence is what is known as. And normally this action is the time, it depends on the space dimensions of space that you work in. But generally, if you work in ordinary quantum mechanics, so you don't have any spatial dimensions in the spatial time, then it will just be the integral of the ground. It depends on x dot and x. Generally, it could also depend on time, but we will ignore that possibility. So this is where we start. If we take this action and we apply the so-called Euler Lagrange equation to this, it is such as Neutron. So basically the idea is, when you think about Newton's equations, what you try to do is to write down an action. And when you minimize or externalize this action, which is actually Hamilton's principle, you get back your cohesion function. Now this is all classical, so how do we quantize? To quantize the theory, all we do is we take for the path integral, so we integrate the sum over all paths and we weigh it with this function. Okay, I should actually write this function. So basically all I do is I take all possible configurations of the path x. You can imagine I start at path x here, start somewhere, end somewhere, and I just look at all possible variations. And I sum up all these different contributions and I weigh each one with this space. And from this quantity, I actually want to introduce something more. It introduces your source terms. We call this the generating functional. It's not that important. I write a little bit of technicalities for those of you that are interested on the board, but now this will be the last equation that you will see. So from this quantity, we can actually compute everything for the quantities. We can compute transition probabilities, transition rates, scattering cross sections, everything we want. So this is the fundamental quantity, the so-called generating function. And this is how we quantize the theory nowadays. So come to me, bring me your favorite Lagrangian, I compute an action, and I compute this thing, or I try to compute this thing, because this thing is a horrible thing. It's not doing all of Bell's fine, but nevertheless, we can proceed along this way and compute a lot of the things that we discuss. So that's a very simple recipe for quantizing the system. So, for example, if you now want to do a normal quantum theory, you would say linear Lagrangian density. So here's some Lagrangian density, L. You write an action. You work in free space in one time. Write the action is this, and you apply exactly the same recipe. So write a generating functional, which is now the sum over all possible field configurations. This Lagrangian will be a function of the fields, a function of field configurations. Lagrangian is a function, action is a function, so the radius is this, apply, just like that. So there's no difference between simple one-dimensional or simple quantum mechanics and quantum field theory. The only difference is that here we actually have fields that is spin in space and time, like quantum mechanics with fields between over here. All right, so this is the story, and I tell you this quickly because I want to get to the problems of gravity and need to explain this. To explain those problems and need a little bit of history. So this is the way you will go about it. Now, as I said, once I've written down this thing, I can essentially complete the detail. However, there's a problem. When so let's say I want to do quantum dynamics. Then I write down action for Maxwell's field, and I couple it to some matter fields, and write this all thing down, and I start computing. But what I discover when I do this is that the results I get are so that's a problem. And why does this happen? The reason why this happens is when you do this computations, you have to integrate over omega. If you integrate omega up to infinity. Now remember, high omega corresponds to short distances. So this means you look at infinite energies, infinitely small distances. And therefore we call these divergences or these infinities ultra-high infinities. So this caused havoc in the 1940s when people tried to build something. Okay? And there were all kinds of attempts to resolve these problems. One of the attempts was by a guy with the name of Schneider, and he was the first guy that actually proposed so-called quantum space, which I'll come back to a little bit later. But then, just before the idea of quantum space established itself, Swinger noted something. He noted that for a large class of theories, a large class of, not so large class of theories, the infinities can be absorbed by recharacterization. Okay, now what this ends up in is, this case, we end up with a finite theory. With a finite number. So that was great. And everybody then started using this idea. This is called the reconciling. And all the field theories we study today, the standard model, so if you do QVD, the standard model is, by the way, is the one which but it's the electromagnetic theory, electromagnetism, quantum dynamics, weak interactions, strong interactions, all these theories are renormalized. Otherwise, we would have just generated garbage. Okay. So, that sounds good. So everybody was very relieved, and the world went on, and people studied these normalizable field theories to answer the basic questions about observations that were made, and of course the results came out were spectacularly successful. But then, the problem came. And the problem that popped up was gravity. So let's talk a little bit about the problem of gravity. Okay, so when people realized this idea of denormalization, they said, oh, great. So all these equations, all these field theories we do, we start with some equation of motion, it could be a Dirac equation, start with an equation, whatever. Write an action that gives us the equation of motion, we plug it into the functional integral, and voila, there we go. So of course there's a very famous equation of motion that was discovered by Einstein in around 1950, and that's the Einstein. The Einstein equation, I will not write it on the board, basically tells you how space-time responds to the distribution of energy and momentum. Right? So it links the energy momentum tensor to the metric, or the geometry of space-time. And there's a loop, so energy momentum affects the geometry, geometry affects the energy momentum, and it's very complicated and highly nonlinear. So great. We have an equation of motion, we can write an action. We say that. This is called Einstein movement action. Actually, both Einstein and Newton wrote this down independently because Einstein and Newton were not actually agreeing. There were a lot of arguments, and Hilbert thought Einstein was a little bit of a fool, and of course Einstein thought the same about Hilbert. But so they wrote down an Einstein-Hilbert action, which I won't write down, and they said, okay, let's calculate. Here we go. Now what came up? Just totally wrong. Everything was divergent. And they said, okay, but let's normalize. Then it turned out we cannot reparameterize this theory anymore, like the others. We cannot find a simple reparameterization to get rid of infinities. If you try that, you actually need an infinite number of parameters. So you either have to live with infinities, or you have to live with a theory with an infinite number of parameters, which is a useless theory. Okay, because I can predict life in very few. Okay, so this was a big problem, and it's still a problem. So gravity doesn't conform to our normal ideas in quantum theory and the normal ideas. We just cannot make a sensible theory out of it. Quantum theory, I should say. There are a couple of other problems with gravity, even classical gravity, that is just one dimension. These are also, in this film, highly under debate. The first is the dark matter problem. So you may have heard of this problem. Now what this boils down to is if you look at the galaxy. The galaxy here, as we look at the velocity at which big gas clouds, because we can observe them, far away from the center of gravity, we look at the velocity at which these big gas clouds are moving, then we find out that this so-called velocity curve as a function of radius here carries in this way. So what happens here, this you can understand, well, because it's moved out, of course there's more and more matter in the field. Okay? So the velocity should go up. This is simply the normal Newton's equations applied to centrifugal motion. That's the equivalent equation. The funny thing is, at some point I have included all the matter in here, and then the velocity should actually start dropping down. If you calculate this, we would use the Newton rules. It should actually start dropping down like 1 over the square root. So what we would actually expect is that it should behave like this. But this is not what you see. You see that these velocity curves back. So basically there's a lot of missing matter. Okay, it looks like there's matter we are not seeing. This is why it's not coming down. And this is the origin of dark matter. So the solution people came up with, it's stuff that we don't see. It's always missing socks that you know that disappears in a packaging material. That's dark matter. But in any case, there's a lot of dark matter. In fact, dark matter makes up about 90% of the universe. Okay, I think it is dark energy as well. I will mention that as well. We have acid energy about 94%. But this is a problem with classical gravity. And the other problem with classical gravity is that of dark energy. Just check my time. Okay, instead of dark energy, dark energy is what we have discovered very recently, is that in contrast to what has been believed for the past almost 100 years, that the universe is expanding at a constant rate, we have discovered using supernova explosions, as simply standard numbers because we understand them very well, so we can estimate the distance that they are from us quite accurately. We have discovered that currently the universe's expansion is accelerating. That's strange. So what is happening for a long time apparently the universe expanded at a constant rate, it's accelerating. So it's like gravity is now acting like a repulsive force, pushing the universe apart. We don't know why. This problem is closely related to the so-called cosmological constant problem. And this is again, this is why I mentioned these problems, this is again closely related to the problem of vacuum, unity of vacuum fluctuations, or vacuum. In a vacuum, just like a normal quantum mechanics, you'll remember if you have a harmonic oscillator, even in a ground state there are fluctuations and there's a finite limit. And here also there's a finite limit. So what is this is actually a very important point that you should not forget. The big difference between ordinary quantum mechanics, in ordinary quantum mechanics, when we put in normal quantum field theory, if I shift the energy of the system, it doesn't matter. Right? It's like we always say, whether you measure the energy, potential energy from here or from there, it's the differences that matter. Right? Gravity is different. Because gravity is even sensitive to the vacuum. It matters what a vacuum is. This is what makes gravity so difficult. Another problem is, we can try to compute this vacuum energy. And voila, if you do that, you find out that you are 120 orders of magnitude out of population. It's the worst prediction ever of physics. Right? So it really breaks the record in terms of bad predictions. All right. So this problem is actually intimately connected to the problem up there of how do we achieve quantization. How do we quantize it? Right? And it's also, this problem here is also very likely connected to the same issue of not understanding what was underpinning of gravity. So how do we get out of this situation? So this is the current situation. None of these problems have to be solved to, I would say, a satisfactory. There have been many attempts at resolving this. I will just mention some. The first one is what people call modified gravity. So some people will say, okay, let's just keep Einstein's equation and see if we can get things right. So they did that, and you can actually get in this one. But then if you do that, it turns out that you get everything on a sort of galactic scale, you get it right, but on a cosmic scale, everything is right. Okay, so that doesn't seem to work very well. There are people here in the country, at UCT, for example, working on modified gravity. I think it's a delay. All right. The other option is what people call modified Newton dynamics. So some people say, well, you don't know if the laws of Newton apply at all scales, so let's fiddle with Newton's laws and see if we can get it right. Okay? So you can do that, and you can in fact get this right, but of course it's a very ad hoc procedure. You just fiddle with Newton's laws, and again, on long-length scales, you get a problem, and then you have to fiddle again with the laws of long-length scales. So there's no clear understanding of why Newton's laws differ on different scales. So not the average situation. And there, of course, is string theory expression. And they said, you're all a little bit silly. It's all very simple. You just have to do superstring. Now let me just say that you look at superstring theory, of course, this is actually the only consistent theory that we can formulate. And it lives in 10 dimensions. It's the only place where it is consistent. And it's a beautiful theory, and it has a wonderful property. It's the only quantum theory we have that contains a spin 2 particle, which we could identify with the gravity. So when people realize this, everybody got excited. They say, okay, now we have found our holy grail, spin theory. And if you look back in history, you'll see people like David Brewers and those say, it's the only game in town, forget about it, it's just. So what happened to this? Well, unfortunately, it ran into rather some nasty problems. The first problem that it ran into is you have to compactify. We don't live in a 10-dimensional. So 6 of these dimensions have to be pulled up in some other way. So we must one dimension 10 as 6 plus 1. This is our one. The 6 others are in some way compactified. By the way, this is a very old idea. It goes back to people when these are applied in the 1980s. Now, if you do this, you find out for this to be consistent, this 6-dimensional world or 6-dimensional part of the manifold is actually must have a very specific property. It must be a so-called Kaluba-Yau. And we can enumerate the number of Kaluba-Yau manifolds. And there are about 10 to the 500 of 6 dimensions. Roughly. There's still a debate about whether this is 450 or 500 or something like that, but the problem is we have no way of deciding which one of these possibilities is realized in the universe, which one of these possibilities. There's no mechanism of distinguishing between these. So there's no condition like the one gives you a lower energy or anything that tells you which one is the right one and which one is the wrong one. In fact, it's not even clear that our universe is one of these simplified possibilities. And each one of these worlds look different. They have different particle content, they have different forces acting in them, etc. So people came up then, David Bruce in particular, with the idea of multiverses. He said, well, there are just many universes, 10 to the 500 of these. And it just so happens that if our universe didn't look like the one we are in, then we wouldn't actually need to see the difference. So don't be surprised that the world looks the way it is. This is, of course, very famous, so-called anthropic principle. Okay, things look the way they are because they can't look differently than we would be. I don't like that sort of philosophy. Fortunately, most of the students also don't like it. But of course, if our world is not even contained in this, we have a serious world. Then we wouldn't exist at all. Okay? Right. So this brings string theory into a rather distributable situation. There's another problem now very recently in string theory, which is that supersymmetry seems to be excluded by the LHC. We haven't seen any sign up to this point of supersymmetry, and we're already below or above the thresholds where we should have started seeing it. So, like many people say, supersymmetry is in the ICU. It's almost there. And these are all supersymmetric fields, so they don't seem to be what we see. So what now? So basically it means we are back to square one. Supersymmetry failed, or string theory failed, or string theory failed, then we are back to where we started dynamism. We just don't know what's going on. But there is fortunately an alternative, and I'll just now very briefly mention this. Okay, this alternative is what we call quantum. There are different quantum space or noncommutative space. Or also often called noncommutative geometry. I will use that. So let me explain the rationale. And there's a very famous paper by one of the leading, so some of the leading people working on the algebraic approach to quantum field theory, which have argued this, and I would say it's really a very compelling argument. It's not a proof, but very compelling. Okay, but let me give you the gist of this idea that I have. They said, suppose we want to localize a particle somewhere in space. So here's a particle, and we want to measure its position, find its position. So what do we have to do? We're sending a probe. Normally it would be like a photon, of course it could be other particles as well. And it scatters, and we detect it, and then we can see, okay, what is the position. Now, of course, we can only resolve the position of this particle up to a limit which is determined by the wavelength. If the wavelength is long, this is just because of the diffraction essentially, but if the wavelength is long, we can resolve the position within a certain limit, the wavelength. We make the wavelength shorter, we can resolve it better and better. But there's a problem with this. If I push up with if I push down the wavelength, or push up the frequency of this incoming light, the particle, it's a particle, this was of course the roller wavelength, the quantum wavelength. If I push that up, I get a higher and higher density energy. Because remember, the energy of the photon scales by the frequency. And similarly, if a particle, its energy goes like a square, or 1 over the wavelength, so that becomes big. Now, Einstein has taught us, if you put too much energy in a small space, you generate a gravitational instability. You collapse into a black hole. Okay? So what will happen if you try to do this? What will eventually happen to make the energy so big, this area you want to probe will collapse into a black hole, and there's a horizon that you can't see anyway what's going inside. Okay? So it's really a senseless question to ask, can I detect the position of this particle to an arbitrary distance? Gravity tells you you can't. Right. So the conclusion is, operationally, we cannot measure the position of a arbitrary. We just cannot do it. Yes.
So does this argument not presuppose some things about quantum gravity already?
No, this is absolutely classical gravity. This is classical. Formation of a black hole, gravitational, that's classical. Doesn't. What might happen is, of course, that these singularities get washed out by quantum effects. But at this point, this is purely classical. Okay. So, what can one say now about this? Does this sound familiar to me? This idea that I cannot measure certain things in arbitrary operations. Where have we encountered this? Quantum mechanics, right? It says that you cannot measure position and momentum to an arbitrary accuracy. Now, why not? Because they do not do. So what people say, okay. But listen, so let me just capture this idea that we cannot measure, because of gravitational instabilities, we cannot measure an arbitrary accuracy by saying that, so let's restrict ourselves now to 2D, by saying that delta x minus delta y must be larger than equal to something equal constant. Theta, which of course has the units of interest. Okay? So I bring this in. How will I do it? I do it by saying that x and y coordinate like any normal. So I cannot measure x and y simultaneously to an arbitrary. Right? That's the simplest solution that we can imagine. What is nice about this solution is I don't make any assumptions about what is happening beyond this length scale, this theta or the square root of theta. I don't say anything about what is happening beyond that, because it's senseless. I can't say anything about it because I cannot cover it in physics. So the default law is that theta is of the order of the Planck length squared. Planck is about 10 to the minus 35 meters. So you can see this is a very tiny mass, 10 to the minus 35. It is 20 orders of magnitude smaller than a proton. Right? Proton is about 1/30, 10 to the minus 15 meters, so this is 10 to the minus 35. Good. Now look at what is happening here. This is actually a possible way where string theory will work. Because what is string theory is that when they do string theory, they assume a certain structure shorter than a clumping. They said I put a little string. So they introduced the short length scale as the length of the string. And they gave dynamic string. But they are then talking about some dynamics beyond the Planck scale, something, a specific theory beyond the Planck scale. Now, of course, these theories need not be unique. I can't even say what happens beyond the Planck scale. So it's very likely, and in fact, if we introduce the so-called normalization of nuclear ideas, which I cannot discuss now, it's quite straightforward to see that such theories cannot be unique. So you can write down infinitely unique theories, that you can't say anything about really beyond the Planck scale, but far away in non-length scales will all look the same. So it's very likely that the problems here, string theory, has to do with the fact that you make a certain assumption about what happens beyond the scale that you should not be talking about. Okay. Well, this is not the case here. Here we just plead ignorance. We just say we don't know. Okay, and we capture it by saying we cannot measure it. A very neat solution. And as I said in this paper, if you are interested, Doppler, Favour, and those guys, they also mentioned was a very complex field theory. They argue this point very, very concisely.
Is there any way to preserve Poincare symmetry?
Okay, good question. Not in this setup here, but I will mention when I will not talk about the relativistic theories today. I will just talk about one of the theories. Because the same problem crops up with rotational symmetry, and in fact you can if you impose the appropriate commutation relations in Poincare sums with the mechanical system. I think you are thinking about what is called Minkowski space, where the Poincare invariance gets broken. And people are looking for such attacks also, experimentally. But I doubt very much that, let me phrase it this way, that breaking of the Poincare symmetry is based on a certain assumption of the commutators. And it's a very naive assumption. And you can write down commutation relations that will not break the Poincare invariance, and you can still go on with your life. Okay, so breaking of Poincare invariance is not an essential issue, and one can fix it actually in different ways. So it will be formal Poincare process. But let's leave that aside. All right. But now comes the question. This is all good, but suppose now I want to do quantum mechanics. Right? And I take this idea in quantum mechanics seriously, namely that there's a short length scale beyond which I cannot say anything, or non-commutativity of quantum mechanics. How do I do quantum mechanics? On quantum space. The name quantum space here is a little bit of this is why I actually prefer to use the term non-commutative. It's a bit of a misnomer. There's nothing quantum really about quantum space except that things are not commuting. H bar doesn't feature. At this point, H bar doesn't feature. Only this feature. Only when you do something in quantum mechanics, H bar does. The answer to this question is actually, we struggled with this question actually for some time. Few years actually, and then when it came to us, it was very simple and obvious, and you can moment you say, after that means it's stupid. What we do is the following. If you think about ordinary quantum mechanics, let's say we do quantum mechanics in 3 dimensions. Now, Hilbert space is the space of square integrable wave functions. Okay? So now we want to introduce a similar notion. And the idea is very simple. What we do is we first introduce something that we call a Hilbert space that we call configuration space. And this Hilbert space, on this Hilbert space, we introduce operators like x and y that commute or satisfy these commutation features. So this is what we call a realization of So there are operators acting here that satisfy exactly these conditions. And then what we do is you build a new unit, which is the quantum unit space. And this consists, and this is a very well-known theorem in operator algebras. This quantum Hilbert space consists of, out of all the so-called Schwarz class or Hilbert suite operators. So they consist out of all operators psi acting on H, so that's this and this, and with the property that if I calculate this, this is the analogical condition here, that the integral one can show this is the Hilbert space, it has all the properties that we want. And then we just start with quantum mechanics in this Hilbert space. Nothing new. The only thing that is new in this world is standard quantum mechanics. We just emphasize it. People think we are doing new quantum mechanics. We are not. We are just representing quantum mechanics on a different Hilbert space, which is in any case completely allowed by the basic absolute. Yes?
So is this statement just that the bounded linear maps from a Hilbert space to itself forms its own?
Sorry, I didn't quite hear.
So does this statement basically just state that the bounded linear maps from a Hilbert space to itself forms its own Hilbert space?
Yes, correct. Well, if it satisfies this condition, not any operator. So it's not even just in bounded operators, it is real class Hilberts. Okay, so it's actually more restrictive. So you can actually translate this also into functions. It means that this kind of Hilbert space is built out of Schwarz class functions. So it's functions that are absolute value that are, that's the word I'm looking at, that are square integrable up to all orders. All derivatives are square integrable. Okay, so it's actually a smaller class than just your bounded derivatives. Okay, but yes, so that is the statement is that all operators satisfying this. This is obviously bounded. So these operators are bounded, but they're actually more restricted. And they form a Hilbert space. The only thing that you need to be a little bit careful about is how do I do a position measurement? Because obviously position is not commuting with each other. So I can't think anymore about doing an X and a Y measurements simultaneously. But that concept is very easily taken into account by what we call weak measurements or positive operator value measures. I want to talk more about that. But it's quite easy to accommodate that problem and still talk about position measurements in everything like you do in standard normal quantum. Nothing really actually coming in. Okay. So this is just very briefly the idea. So what we do essentially is to replace wave functions by operators. Okay, so this is why this is what some people would call matrix models. Some people call it matrix models. We call it noncommutative quantum mechanics. There's a little bit, it's not quite matrix models, but it's closely related to matrix models. You may have heard also about the term M theory that was phrased by, I think it was Lenny Ziskert, that phrased the term M theory, which is supposed to stand for the mother of all theory. So it unites all these different string theories. But Lenny said no, it stands for matrix theory. So there are many people that believe that the solution to quantum gravity is actually matrix. And what we are working with is actually a type of. So it connects very closely to this idea of matrix models as a possible way of resolving quantum gravity issues. Okay, let me now just end up with telling you in 5 minutes or so, if you take this point of view, what happens? So rather remarkable things happen. And I'll talk now about the real worlds, 3 dimensions. Now, there was a question about concave symmetry. So, if we assume the normal kind of these kinds of computation relations will break it. But what we do is we take SU2 computation relations. And if you do that, you see the left-hand side and the right-hand side perform exactly the same like the limitations. And this resolves the possible problem with breaking of limitations. So this turns out to be a fully rotational invariant field. Nothing strange. Okay. Some things that happen. The first funny thing that happens is that you discover if you have a finite volume in space, there's no longer an infinite number of states inside that volume. Because what happens is each state effectively occupies a volume number. It's the same thing that happens if you work with phase space and you have a particle in a box, momentum is discretized, and then you find that the volume of a little cube or state occupies is of course 2 pi over L cube. The same thing happens here. So the number of states in this space, in this volume, is basically volume up to invariant things. What does this mean? There are several consequences. The first is that you cannot get an infinite energy. Energy cuts off. Even a free particle doesn't have an infinite energy. It stops something. That makes perfect sense. How can we actually think about infinite energies? Given that when we make the energy density large enough, we generate gravitational instability. So from a gravitational point of view, the idea of infinite energy is absurd. This conforms completely with that notion and says you cannot have an energy categories. Okay. The second is momentum is also cut off. There's a finite momentum. Momentum cannot be used for the same reason. Another thing that happens, which is quite cute, is imagine I have a finite number of states here, and now I start throwing fermions. So these are things that exclude each other. So I can put one fermion in such a cell, but not more than one. You can fill this exclusion. So if I start filling the states in this volume, what will happen? Well, it's also full. If I fill all the states, I cannot put anything more. Right? So now imagine the following scenario. I have a bigger volume. I have a lot of particles, then I start squashing them. And now they start filling, I get less states, I start filling all the states, and eventually I get to the point where all the states are full. What is going to happen to the pressure? It's going to blow. The pressure is going to go to infinity. This is a sharp contrast to what we have in normal quantum mechanics, where the pressure we are talking about there is the so-called degeneracy pressure. That is finite. Okay? So, what we can do now, what we did, is you can work out, for example, from a star, what is the mass radius motion? Not such a nasty calculation as you can see. This is done non-relativistically, by the way. And then what we find is like this. So, as you increase the radius, initially the mass grows, then it becomes, the gravitational force becomes big, it starts shrinking, and eventually it becomes actually a tightly compact ball, where everything is squashed into a finite sheet. Now in the normal situation, there will be a point here where the degeneracy pressure cannot cancel with gravity anymore, and then the star will collapse into a black hole. This doesn't happen here. It just keeps on adding matter to this ball. But of course, this ball of matter, the solid pack of matter, is hidden behind the event horizon. So we don't see it, but it gives a possible suggestion of what will look like beyond the event horizon. Okay? What is quite remarkable about this as well is if you think about entropy, if this ball is solidly packed, the only freedom you have to excite anything is on the surface. So, because of that, what you would expect to happen is that you compute entropy. The entropy doesn't go to volume, it actually goes to the surface, which is exactly what happens for black holes. This is the so-called famous Hawkins-Beckett-Stein. So the entropy of a black hole goes like some constants times the area. So a lot of interesting things happen. One of the other remarkable things that happen is that if you work on a classical dynamics, so you start with the quantum theory, like I explained earlier, you get an action, you write down equations of motion, then they look almost like Newton's equation, but they are modified. Remember I talked about modified Newton dynamics? So you actually get a modified Newton dynamics. And this modified Newton dynamics has a remarkable property that there's a maximum velocity as an object value. Okay. So if you work out the velocity curve, it does exactly that. And it gives you the maximum velocity. So even that seems to fit into the picture. Of course, these ideas are still very speculative and rough, but there is a lot of interesting stuff that come out that may actually be observable in years.
Why doesn't producing a maximum velocity basically force up the velocity curve? Because usually classically we expect the velocity curve to be lower than what we observe.
No, so basically what happens is your curve goes up, but now there's a maximum velocity that you can reach. So those clouds out there can't move faster. So basically they will just move to the maximum amount of velocity.
But you still need more matter.
Sorry?
You still need more matter, otherwise it will still drop down as fast.
No, this will just it won't come down. It won't come down.
Due to a maximum.
Yeah. Even if you include all the mass. If the mass is large enough that you include, so that the velocity out there exceeds the maximum, it will stay flat all the way. Alright. You do still need missing matter. So it doesn't get rid of the dark matter problem, but what it does is quite interesting. It doesn't matter how you distribute the dark matter in the galaxy. You can plug all of this stuff into a big black hole in the center of the galaxy. And it will be used in a second. And that will be good enough. And one of the problems with dark matter now is that we have to quite fiddle with the distribution of the dark matter in the galaxy to explain the velocity curves as well, which is a bit unsatisfactory also. But this is quite robust. It doesn't matter. And we know that many galaxies have very massive black holes at the center. So it's speculation, but maybe if there's enough mass in the form of a black hole that we don't observe at the center, it is quite plausible that this scenario may come out. Here's a question.
I just wanted to check, or I wanted to ask, would an analogy of what's happening with the flattening of that velocity be like if you have, for example, an amplifier where you amplify a signal above the roof, you get distortion and something. It's the same thing. It actually
and it will cut off your signal. Yeah, exactly. It's exactly the same thing basically. So there's a ceiling to what you can do, and the moment you reach the ceiling, you can't come down as well because there's already enough mass here to keep you up. So this is basically a very quick and dirty and rough exposition of the ideas that we are working with. But I am quite excited about the idea of quantum space and non-commutative space. I think it has features that are very desirable. I wouldn't say it has all the features that we want. And it will probably turn out that the models we are building now are not correct and not really fully describing the world as we see it. But I think it resolves so many fundamental issues that the message must be in some sense fine-tuned. And I really think that this is a very likely scenario that will resolve for us the problem of quantum gravity. Let me just one final conclusion. this debate about quantum gravity has gone so far now that we are even fighting about whether gravity should be quantized in the first place. So you may know that if one of you from the Linder brothers, he's working on another picture of idea that quantum gravity should be quantized. That may be possible as well. We simply don't know where it's going to go. So if you thought everything is done, there's a whole desert out there which hasn't been explored yet, and many, many possibilities still open to us. Okay, thank you.
Wanneer is dan baie dankie.
Just